Let's continue to talk about the C fundamental types. There will be other types later on, like pointer types and struct types and enum types. But for the moment, we're going to concentrate on a fairly simple set of types. Maybe not that simple. And our early computations will do a lot with int and double and char. And intuitively, you can understand that a char might be a special character like A or a capital N, or the character that's the digit 5, which is going to be different than the value 5, or an unprinted character that moves your screen a line, so that's represented by \n. So the characters can represent what's called the ASCII table of characters. It's typically all the lowercase, all the uppercase, punctuation, operator characters, digits, and some special characters like new line. The integers are pretty much what you're used to since grade school. They're numbers like 0 or -3 or +77. And then finally, there are doubles. These are more like the scientific notation. And there you get numbers like 1.245 or 3.2 with an E, which designates that something is an exponent. The exponent is a power of 10, so it's 10 to the 5th. So that's going to be 320,000. Then we're going to allow the fundamental types to have further modifiers. The two critical modifiers are going to be unsigned and long. The idea of unsigned is going to apply to strictly the integers, and that's going to mean that you're going to rule out the negative numbers. Long is going to apply to both the integers and to the doubles, and they're going to mean, well, we might have a range, which typically for the integers is plus or minus 2 billion, and we want a longer range. So that will increase the range of those numbers significantly, and we might need it for a bigger calculation over bigger numbers. Finally, the same thing is true for doubles. We're actually going to have 3 kinds of doubles. We're going to have float, double, and long double. And on a typical implementation, these are going to be longer and longer, and therefore capable of storing a bigger and bigger number. Well, it's not like mathematics. It's not like you can imagine a number like pi, in which there's an infinite number of decimal places. So the mathematician's conception of pi is potentially this infinite string. That's not doable. The computer memory is a finite resource. It's organized in terms of bytes. A byte is a unit of memory, which is conventionally 8 bits, and 8 bits can only store so much information. Basically, they can store 2 to the 8th. So here's a number that could be stored. Typically, these things are bits, so 0001010. Remember, computers are binary, and they store bits. They store them somehow electronically, magnetically, unless you're going to work with some kind of fancy quantum computer. But on all our actual digital computers, a modern digital computer uses a base 2 designation and bits to represent whatever you need to represent when running a piece of computer code. Well, if you look at this, this is the zeros place. This is 2 to the 4th, 2 to the 3rd, 2 to the second, 2 to the first. Excuse me. So 2 to the no, I have this wrong. This is 2 to the fourth, which would be 16, and 2 to the 2 squared is 4. So we're going to actually get the number 20. Very easy to make a mistake if you're not a computer. On a typical machine, an int is 4 bytes, and an int can be used to represent between roughly 2 billion, minus 2 billion, and plus 2 billion. This is more exact. So actually, this is equal to 2 to the 32nd minus 1. And that shows you 4 bytes can be used to store 32 binary digits. One of the digits is going to be used for the sign, so that leaves 31 digits for everything else, and that's why this can be roughly 2 to the 32nd minus 1. Now, when you write your code, you need to know what is representable. The way you can find that out, you can see what a type will store by using a built-in operator, one of your keywords in C, using sizeof. And we're going to show that. So one of the funky things about C is certain things can be system dependent. Why is that? Because C attempts to be efficient in relation to the underlying computer. So it's not attempting to have universally the same semantics, because some computers have very big word sizes and some computers have small word sizes. And C wants to run efficiently on a computer that has an int size of 2 bytes, as well as a supercomputer that might have an int size of 2 bytes, as well as a supercomputer which might have a 16-byte int. So you do have to know and realize that you're running on a particular system, and you can even, if you're a very sophisticated programmer, ensure that your system has sizes that are appropriate for your computation. And you can look at that dynamically by using this sizeof operator. You can see it here. There's a sizeof print, a sizeof long int, a sizeof a char, and here you see you can use a variable. I could have said char, but I can also use the variable. So sizeof will operate on either a variable name or on an actual type name. Here's float, double, and long double. And let's execute that program for the system. It's a Macintosh system. And there, on my system, an int is 4 bytes, a long int is 8 bytes, a char is 1 byte, a float is 4 bytes, a double is 8 bytes, and a long double is 16 bytes. So you should go and try that on whatever system you're using.